Allora, today's speaker is Fabio Cumbo. Fabio is a software engineer. He took his PhD in computer science and automation engineering. And he currently has a postdoctoral research position on the Faculty Lab in the Lab and Research Institute of Cleveland Clinic. His main research is bioinformatics, and today he will present the work computing with high-dimensional vectors, theory and application in bioinformatics. Okay.
All right, thanks Daniele for this introduction. Thanks the director for inviting me today. I'm going to talk about hyperdimensional computing. We are going to look at some theory. We're going to look at a few applications in bioinformatics. So let me spend some word for the background, just to introduce you to some basic concepts that will hopefully let you understand what hyperdimensional computing really means and how it works. So with just a couple of sentences, we could say that hyperdimensional computing or high-dimensional computing is a system of computing that operates on high-dimensional vectors. So this means that algorithms are based on operations on vectors. So the main idea behind this concept of working with high-dimensional vectors is not really new. So everything started with von Neumann with his manuscript, The Computer and the Brain. 10 years later, with the perceptron of Rosenblatt, and on the 70s and 80s with artificial neural nets, until a more recent holographic reduced representation. So if this is not a new idea, why are we talking about this today? So just because today we have the right technology required to build very large systems that can work accordingly to this theory. So we just say that hyperdimensional computing is a system of computing that operates on high-dimensional vectors, and algorithms are based on operations on vectors. So let's define our set of arithmetic operations behind this way of computing. So everything is based on 4 very simple operations: the addition, multiplication, the permutation, and the comparison of vectors. So we can element-wise add 2 vectors. We can multiply vectors, applying the exclusive OR element-wise. We can also permute a vector, which means rotating the vector n positions by n positions. And we can finally compare 2 vectors just by estimating their similarity, computing, the Hamming distance or the cosine similarity or other similarity measures. So let's consider now this very easy data structure here at the bottom of the slide. This is just a dictionary, a mapping between variables x, y, and z, and values a, b, and c. So according to the hyperdimensional computing paradigm, everything must be encoded into random high-dimensional vectors. So I just want to point you to this research article here proposed by Dr. Pentti Kanerva in 2009, in which he deeply explained the arithmetics behind this computational paradigm. So, okay, we have this data structure. Let's start with the encoding. Let's start trying to represent, to encode this data structure into a high-dimensional vector. So according to the dictionary, we know that x is equal to a. So we have to represent both x and a as vectors, binary vectors in this case. So we say that x is equals to 8. So let's bind this vector representation together using the multiplication operation, which just consists in applying the element-wise exclusive OR. So we can do the same with the other 2 variables in the dictionary by computing the multiplication between the vector representation of y and b and the vector representation of z and c. So we also know that these 3 mappings compose H. which is the variable that represents the dictionary. So we can collapse all this information together into a single vector just by applying the addition element-wise between the vectors that we just computed. So we can finally convert the computed vector into a binary vector by applying some kind of majority rule. And so, if the number in a specific position is divided by the number of vectors that we sum together is greater than 0.5, we just set 1. Otherwise, it's 0. Very easy. So we can encode information. We ended up with just a single vector representation of our data structure. So how could we retrieve information from this vector? How could we decode information from this vector? And here we can even more appreciate the power of the binding operation on the retrieval of values from the hyperdimensional compute, the hyperdimensional representation of H. So if we bind again H with X, we can indeed produce a new vector, which is pretty similar but not identical to the hyperdimensional representation of A. We will see this in the next slide, why the produced vector is not identical to A. And we can verify that the produced vector is almost A by searching for the closest vector among the hyperdimensional representation of the values A, B, and C, just by computing the Hamming distance, the cosine similarity, whatever other similarity measure. Okay, so let's have a deeper look at what we just seen. We were able to compute the hyperdimensional representation of our data structure H. We saw that retrieving information from H, which means decoding H, is extremely easy, I will say. So in the previous example, we saw that binding H with X produces a vector, which is very, very similar to A. So let's see why it's not A, but something very similar to A. So let's decompose the binding operation between X and H. We can say that H is the sum of 3 bindings: X with A, Y with B, and Z with C. So we can bind all of them by X, because the exclusive OR distributes over the addition. And we can also say that X and X, in this case, essentially cancels out, because the exclusive OR is its own inverse. And we can say that X, Y, and B, and X, Z, and C, these are just noise, I will say, which means that these bindings produce vectors that are dissimilar to any other vectors, and they are approximately orthogonal. So the final result is very similar to A. So when I'm going to compute the cosine similarity, for example, since these are approximately orthogonal to the input vector, the similarity is they are completely dissimilar from my input vector. So we just ended up with A. So it's not really A, but it's something very similar to A. Okay, so we can conclude this introduction to the theory behind the hyperdimensional computing. It's very easy, and with this set of observations, right? A randomly chosen vector is dissimilar to any other vector seen so far, because they are approximately orthogonal. The addition produces a vector that is similar, and the multiplication and permutation produce vectors that are completely dissimilar to the input vectors. The multiplication is invertible, this is very important, and distributes over the addition. Also, the permutation is invertible, and it distributes over both the addition and the multiplication. And the multiplication and permutation preserve the similarity. This is very crucial when computing the similarity. So let's see another example. This is exactly the same example in the Canerva's paper, where he firstly introduced the concept of hyperdimensional computing. So what's the dollar of Mexico? We want to determine a currency of a specific country. Let's try to extract a few information from this question. So we know that dollar is in general the currency of the United States, right? While peso, which should be the answer to our question, is the currency of Mexico. So let's try to encode this information following what we just learned. So encoding everything into random high-dimensional vectors. So here, currency, country, and let's also add capital city, just to add some other additional information that help us shape the reality we want to encode, just to make it a little bit more tricky for the retrieval. And well, all these variables are vectors. And what about their values? USD, which means dollar, or PES, peso, are both vectors. USA and Mexico are both vectors, and Washington, D.C. and Mexico City are both vectors. So our goal here is to try to build a vector representation of the two countries. So let's start with the United States. We combine the vector representation of the variable country with the vector representation of the value USA. We combine the vector representation of the variable capital city and the vector representation of the value Washington, D.C. And we combine the vector representation of the variable currency with the vector representation of the value USD. Just remember that binding two vectors is equal to applying the element-wise multiplication between these two vectors, which means the element-wise exclusive OR. And we can finally bundle, which means sum all these vectors together, resulting to build the vector representation of the country, the United States. And we can do exactly the same for building the vector representation of the country Mexico. So let's say that we have a vector representation that we want a vector representation for the world we just defined, composed of just the United States and Mexico in this case. We can simply bind these two vectors to produce our final vector symbolic architecture. So let's try to answer our question, what's the dollar of Mexico? We have a vector representation of our architecture that we defined as the binding between the vector representation of the two countries, United States and Mexico. And well, if we decompose these two vectors, the result of the binding is something like this one, where country binded with itself cancels out because of the exclusive OR operator, and same for capital city with itself and currency with itself. So we ended up with these bindings here of just the vector representation of the values. So what happens if we try to bind the vector representation of USD with our vector representation of our architecture? So this produces a new vector, which is different, but very similar to the vector representation of PES, peso. Some of you look a bit skeptical. Let's do something here. So let's do a quick demo. I'm not going to ask you to open your laptop. Just follow what I'm going to do here. We are going to use HDLib. HDLib is a Python library for designing and building vector symbolic architectures. Something we published on the Journal of Open Source Software a couple of months ago. It's a Python library, so let's open our terminal. Let's invoke the Python interpreter, and there is a module which is called space in HDLib that defines the hyperdimensional space and hypervectors. So let's import these two classes. So from hdlib.space, import vector and space. So if you go to the wiki page of this GitHub repo, you will see a few examples, and we also have what is the dollar of Mexico example. We are going to follow this wiki. So as you can see, we can import vector, we can import a space. So let's define a space. Space is a new object space with a specific size. Here the size is actually the length of the vectors. And the space actually just acts as a container for our vectors. So size of 10,000, so there is a reason behind this 10,000, so we will go to this later. And let's see that we want to define to host bipolar vectors instead of binary, but it's actually the same. All right, so just to follow the what's the dollar of Mexico example, we are going to build a few vectors. So let's say that we have variables. In our case is the name of the country, the currency, and the capital city. So here called NAM, MON, and CAP. And we have values. So in case of the USA, it's USA, dollar, and Washington, D.C. In case of Mexico, Mexico is the name of the country, peso, and Mexico City. So let's define this list of, this is just a list of string, right? But we could invoke the bulk insert method of the object space that actually takes an input these strings, and for each of them create a random vector and add these and automatically add these vectors to the space. So we are going to use the binding and bundle operator, which are part of the arithmetic module of hdlib. Let's import them. Okay. And here is what we've just seen in our slides, right? We are going to build a vector representation of the country USA and the vector representation for the country Mexico. So just by binding the vector representation of the variable name, the name of the country, and the vector representation of the value USA, and again the vector representation of the variable capital city with the vector representation of the variable of the value Washington D.C., and the vector representation of the variable money currency with the vector representation of US dollar. And we can finally bundle, which is add all these vectors together to build the vector representation of the United States. And same stuff for the country Mexico. We define these two, we have these two vector representation of the countries. We could bind them together to build our vector symbolic architecture. That's the vector representation of our world, which is composed of just the United States and Mexico. So we say that we could finally bind, in order to answer our question, what's the dollar of Mexico, we could simply bind the vector representation of US dollar with our vector symbolic architecture. So this will produce a new vector that we hope it will be similar to PES, peso. Let's see, we could invoke the method find of our object space that will automatically search for the closest vector in our space. So find guess path, and this is the closest vector. Let's see, closest of 0. Is it PS? It is. All right, seems working, right? Okay, so this is our library. If you want, you can play with this library to build your own architectures. But all right, let's come to the slides. Let's come back to the slides. So what could we do with this kind of architecture? So we asked ourselves, could we maybe build a classification model with this? Of course we can. So let's define our algorithm. Let's imagine we have so let's define our problem. We have a data set, we have a matrix with a certain number of samples on the rows. We have a certain number of features on the columns. That's our data sets. These samples are organized in 2 or more classes, and we want to do prediction. So we say that in hyperdimensional computing, every atomic element is associated to a d-dimensional vector. So in general, a data set that the observation value can be highly variable in a data set. So considering, for example, a data set with numbers, with a single digit after the decimal point, so ranging maybe from a minimum of 0.1 to a maximum of 0.9. So we need to encode every number in this interval with a hyperdimensional vector, with a total, in this case, of 9 vectors. So all these vectors represents our data dictionary. Without the dictionary, the classification model is completely useless. We will not be able to since these are random vectors, we are not able to distinguish, to come back to the original numbers without a dictionary. So the set of encoded vectors, which represent the content of our data set, and represent the data dictionary of our model, is also called a set of hyperdimensional levels. So we can start by processing our experiments by grouping our samples. We need to build a vector, and we finally need to sum all these vector representation of the samples together to create a hyperdimensional representation of a class. And well, we create the hyperdimensional representation of an experiment by encoding the features content, so that we previously encoded in our data dictionary. And we are also able to encode the position of a single feature in the data set just by rotating this hyperdimensional representation n times, with n equals to the position in which this feature is located in the data set. Just imagine a number in your table. You could I mean, this number could occur in different position in the data set, right? But the position of this number is really relevant. It's the feature. We need to take into account the position of the number under a specific feature. So we have a vector representation of a sample for a specific class, and we sum this vector with all the other vector representation of the other samples that belong to the same class to build the vector representation of the class. There is a problem now. So the more vector we add, the more noise we introduce in our model. So how could we minimize the model, the noise? With a process that we call retraining. So what does retraining mean? It means that we have the vector representation of a class. We iterate over the samples that belong to that class in the training set, those that we use to actually build the class vector, and we try to predict their class. So this means that we are going to compute the cosine similarity in this case between the vector representation of the sample and the two classes in the case of a binary model. Since we use this sample to train the model, we would expect a correct prediction, right? But again, the model is very noisy at this point. So what we do in the case of a misclassification, we element-wise subtract the vector representation of the sample from the incorrect class, and we element-wise sum the same vector to the correct class vector, just to decrease and increase the signal of the sample. And we do this for each of the samples, the observations in the training set, iteratively until the error rate doesn't change anymore. So we are not going to be able to further mitigate the error in our model. At this point, we have an optimized model composed of a vector for each of the classes in our data set. So what's next? Prediction. So how could we use our model to do prediction? We could do the same process we did for the retraining. It means that we iterate over the samples in the test set at this point, and we compute the cosine similarity between the vector representation of the sample and the vector representation of the classes that represent the model. So the closest class is the prediction. So we defined the algorithm. Let's look at the data sets we use to test for testing the model. We use TCGA2BED, is a software for the automatic extraction and standardization of the Cancer Genome Atlas genomic data and clinical metadata. We use this software to extract all the public available experimental data of DNA methylation for 3 types of cancer: the breast invasive carcinoma, the kidney renal papillary cell carcinoma, and the thyroid cancer. So as you can see, the number of features here for all the 3 types of cancer is always the same, just because the features are the well-known CPG islands that the sequencing machine is able to analyze. And well, as you can see, we have is in the context of a case control scenario, right? We have tumor and normal samples. So we run our method, our algorithm on these 3 data sets. These are the results in terms of running time and achieved accuracy. And we also compared our approach with BigBOCL, with another algorithm, which is a supervised classification algorithm for distributed environments, which is able to extract multiple models by performing hundreds of classification iterations on a massive amounts of features in just a few hours. And we obtained essentially comparable results. So I just want to stress one point here. BigBOCL has been run on 1 node of the Pico cluster of Cineca. It's the Italian Inter-University Consortium, the biggest Italian computing center, in a multi-threading context on an Intel Xeon CPU with 18 gigabytes of RAM. And while the hyperdimensional computing approach that has been enclosed in a software that we called Chopin2 has been able to achieve the same performances on a commodity hardware, this laptop actually, with an Intel mobile processor, 8 gigabytes of RAM, with no parallelization at all. Okay, so what? So we have a classification model built accordingly to the hyperdimensional computing paradigm. We asked ourselves at this point, could we do also feature selection with this kind of model? There is nothing in literature about this, and it's actually a bit tricky. But there is something we could use around our model that is actually, I will say, the easiest way to do feature selection. And it works with every kind of classification model, and is the stepwise regression, stepwise feature selection. So a stepwise feature selection can be defined as a backward and forward variable elimination. So here we're going to look at how the backward variable elimination works, but analogously, the forward variable elimination works in the same way. So here is a pseudocode, but it's probably better to look at the graphical representation of the algorithm, like this one. So consider that you have your data set with a certain number of samples and a certain number of features, let's say 5 features in this case. So what I want to do here as a first step is to split the set of features and we said we have 5 features, so into 5 models with 4 features each. So every model is going to miss a feature. We build the model in the same way we did before, and we evaluate these models. So we could evaluate them accordingly to their accuracy, or for example, and we can focus on the models with the best scores. So the best accuracies in this case. At this point, starting with the features resulting from the intersection of the features used for building the best models, so let's say the 2 models that got the best accuracies, like in this case, we keep going generating other n models, each with n-1 features. And we keep going generating models with smaller sets of features until we are not able to build models with a good level of accuracies that we set a priori, like 70% in this case. So this is an iterative process. We can essentially assign an importance score to every feature according to the iteration where they get discarded, essentially. So we applied this feature selection technique to quantitative profiles of microbes in metagenomic samples, fecal samples in particular, collected from a cohort of individuals affected by the colorectal cancer in a case control scenario. So the data set is pretty much balanced, I will say, with 101 samples that belongs to the case set, and 92 samples that belongs to the control set. So note that we didn't profile these samples. These are pre-profiled, all with the same quantitative profiler, Metathlon-3. And well, this data set is essentially a table in which you have a row for each sample, a column for each detected microbe species, bacterial species actually. And these plots show an overview of the bacterial composition in these samples in terms of number of species per phylum, for a total of 241 bacterial species. So we run some tests. We say that these are relative abundance data. So we have metrics. Our values range from 0 to 100. So relative abundance data here called array in this table. So we created different versions of the same table, considering all the roughly 200 samples together, but also stratifying the samples accordingly to the sex of the patients, but also accordingly to the age category, adults and seniors. Well, unfortunately, it didn't work very well, except for the unstratified data set, for which we reached 76% of accuracy. So we tried something different. We binarized the data set. All these for all these versions of the data sets by defining the presence-absence profiles of microbes in a sample. So which means that we redefine the table as binary tables, which we found a 1 if a microbe has a relative abundance greater than 0, otherwise it's 0. And well, it worked really well in this case. We reached 83% of accuracy in the worst case and over 90% of accuracy in the best case. And we did also something else. These accuracies are actually the best accuracies reached by the feature selection method under a specific iteration of the algorithm. This is not necessarily the last one. So we looked at the results and we tried to identify suboptimal results in terms of best accuracy with the minimum number of features selected. And the results are in this table on the right side of the screen. And we have been able to select a very small number of significant microbes from classification models that all reached over 80% of accuracy. And we also performed a comparative analysis between our approach and classical machine learning techniques. We used random forest, decision tree, support vector machine, logistic regression, and extreme gradient boosting. And well, in terms of scores, in terms of accuracy, they all reached an accuracy nowhere than the accuracy we reached with the hyperdimensional computing approach, except in a very few cases in which the accuracy is actually comparable to our model. So this technique is also enclosed into Chopin 2. We actually worked also in integrating this software into the Galaxy platform. I already introduced Galaxy in my last talk last week, but since there are people here that who were not here last week, let me spend a couple of minutes introducing Galaxy. So Galaxy is an open source browser-based platform for the management and analysis of biomedical data. It's a worldwide community project. So there are plenty of research groups that actively work and contribute to the development of the platform worldwide. It integrates a workflow management system with the aim of making tools accessible to researchers without any programming skills. Well, I'm a member of the Galaxy team at the Cleveland Clinic, where my PI, Daniel Blankenberg, is one of the first developer and founder of the platform since 2005. So most importantly, it runs over the Access cluster, which is the inter-university high-performance computing cluster in the United States. So you essentially have access to computational resources for free if you run your analysis on Galaxy. And if you ever worked on bioinformatics, for sure you heard about Galaxy. Let's look at a few numbers very quickly. If you are wondering whether it works, whether people is actually using the platform, well, these plots speak by themselves. In 2020, we reached over 2,000 publications citing the Galaxy project, within over 15,000 citations in total. So there is a main server in which the public instance of Galaxy is running. It's actually something that you can download and run on your own server with your own tools, using your computational resources. Well, the first plot here on the left shows the actual number of public servers running Galaxy worldwide. It's over 150 now. Well, there are plenty of bioinformatics tools already available into the platform. Generally, tools are hosted on the Galaxy toolshed. It's a repository of tools, actually wrappers for existing tools. And yes, we reached now about 10,000 tools wrapped and ready to use on the Galaxy platform. So let me also quickly mention that every year there is a Galaxy community conference somewhere in the world. It's a unique opportunity to network with people who are actually involved in the development of the platform, but also with people who are actually interested in integrating their analysis frameworks into the platform. The last conference has been in Brisbane, Australia. The next year will be in Czech Republic. In 2025, again in the US, and then somewhere else out of the States. So coming back to our software, we built a wrapper for Galaxy, so the tool is fully integrated into the platform. It's available on the Galaxy toolshed, so if you have your own instance of Galaxy, you can install it on your server, but it's also available on the Galaxy main. That is the main public instance of Galaxy that is available at this address here. So let's see, there should be a quick video. Just another quick note, at the Cleveland Clinic, we got a 10 years partnership with, let me maybe remove the audio if I can. All right, maybe better. So we got a 10-year partnership with IBM. We installed a quantum computer in our department. is the first quantum computer that has been installed outside of an IBM data center, and it's going to be used exclusively for biomedical research. This is a short time lapse that shows the setup. And well, we currently have an open discussion with IBM researchers trying to figure out how to do hyperdimensional computing on a quantum hardware. So we know it is possible, actually. We have all the ingredients to do that. We know how to encode the vectors in a quantum space. We know how to apply those arithmetic operations, since it's just linear algebra. We know how to compute the cosine similarity between vectors on quantum hardware. So we know it is possible. We actually we are trying to figure out whether the current number of qubits is enough to handle these operations and this amount of data. We currently have 127 qubits. So your question here could be, what is the advantage of doing hyperdimensional computing on a quantum hardware? Well, we hope that in the context of a classification, maybe we hope it could increase the accuracy, but this is just, at this stage, this is just a speculation. So let me go. Okay. Well, I think that's pretty much it. Yes.
Okay, so while doing the classification, talking about the classification, you mentioned about the vector representation, correct?
Yes.
So why not use one-hot encoding in that case? Because it does pretty similar thing like that, right? You just have a sequence. If I'm talking about just a sequence, and then.
But that's simply just another way of representing stuff, right? We are going to take advantage of the mathematics that is behind the concept of hyperdimensional computing by binding and bundling vectors. That's how it works with random vectors in high dimensional space. I think I didn't mention why we use high dimensional vectors. We usually use length of around 10,000, just because these are randomly generated, and the longer they are, the higher are the chance that they are quasi-orthogonal in the space, right? So we are able to differentiate them into the same space.
And you were saying that feature extraction is also difficult in this case. Is it because of the length? Or
no, that's just because of how you build your architecture, right? You combine all these vectors together, but these vectors are random. So how could you extract significant features from random vectors? So we use probably the easiest way to do feature selection. But we are open to any whatever interesting idea you have, if you have something in mind.
Some words, and because I talked about one-hot encoding, people are also trying to do a wavelet transformation, discrete wave transformation for people who are doing for images. Now they're trying also on vectors.
Yes.
So if that is something which can be seen if it works or not. Discrete wavelet transformation. So
okay.
I don't know. It can something that can be tried.
That will be interesting for sure to investigate that. Sure.
Thank you very much.
Thanks. Yes.
Questions. Okay. First, the size of the vector that you use was 10K, right?
Yes.
That is a sort of a rule of thumb, I guess, or have been depends on something.
It actually depends on the number of data you want to encode, but in general, 10,000 means. So since we are building this vector randomly, the length of the vector is crucial for establishing how many quasi-orthogonal vectors are in the space. There are in a d-dimensional space. You have 2 at the power of d quasi-orthogonal vectors. So that lim is actually the number of stuff you could encode.
So you see that, my question. Yeah, right. Of course, this has to do with the fact that you pick them at random, so you have a certain probability of having them.
Yes.
That should depend also on the number of classes more than on the number of objects when you do classification.
Why?
Because eventually, if you have objects in the same class, you may even not care whether they're orthogonal. You may even like them to be equal. So the real information that you want to contain is the differences between classes rather than the difference between elements, in my opinion. And now we come to the other question.
Sure.
When you show the way you bind and bundle and then the bundle
Bind and unbind
bind and unbind
stuff. Yes.
I see that working nicely with two elements, like Mexico and USA.
Yes.
And then you get a certain amount of noise which is generated by the elements.
Yes.
That noise increases sort of linearly with the number of passes that you have.
Sure.
Correct?
Sure. Yes.
Okay.
With the number of vectors that you had to the final vector representation of whatever class, for example.
So this is something that may have an effect.
For sure.
Also on the efficiency, because
for sure
the time that you need surely depend on the size of the random vector.
The time
needed for computing.
Sure. It depends on how. Sure. Yes.
Is that a linear relation or more than that?
I will say yes. I will say.
Okay. Then last question, if I remember. Yeah, the way you generate these vectors.
Yes.
Is there any work on the random distribution when you sample this random set? Is it always uniform, or
it's totally random?
So it's a uniform.
It's a uniform distribution, I guess. Yes.
Okay. And then last, a comment on feature selection. It's really the most. It's a wrapper eventually.
It is, yeah.
So
yes,
it's the only thing you could do.
Well, that's the easiest way probably to do feature selection, and we are not sure it's the only thing we could do. Let's discuss about it.
Okay, going by, I have another question.
Last. Sorry. Why Chopin?
Oh, it's an acronym actually. Every letter stands for domain agnostic supervised classification something. I don't remember exactly the whole.
Okay, thanks a lot. Sorry for the grilling.
Can you just go to slide number 22 once?
Number?
22.
Sure. 22, yeah.
Yes. Okay. So the question is, if you what does this models indicate? Is this like while retraining, how many times you are retraining?
This is the number of retraining iterations. Yes.
What do the models indicate here?
So this is we did here feature selection, right? So let's take, for example, the unstratified data set. This means that we took into account all the samples distributed under case and control classes. We did feature selection. That means that we have 241 species, right? So we started with 241 models with 240 features each, right? Every model is going to miss a feature. And we keep going with the algorithm, with the backward variable elimination, until we do not reach anymore a good accuracy that we set a priori. We set probably 60% here. So we have, at every step of the algorithm, we know the accuracy of our model, and we know the set of selected species at that specific iteration. And this is the best one, which is not necessarily the end of the algorithm, right? And for this iteration, we got this accuracy because we retrained the model 5 times. On the 6th times, the error rate doesn't change anymore. So we stop the retraining process. In this case, it took very long, 19 days to do that. And it generated, I mean, all these 3 of models is composed of over 6,000 classification models. We got over 32,000 classification models in total to do all this stuff.
Ok.
Andrea, una domanda.
Andrea?
Can you hear me?
Yes.
Oh, right. Fabio, first of all, thank you very much. This is the first time I come across hyperdimensional computing. Never knew anything like this existed. And once you start playing around with high dimensions, high dimensional spaces and things, the next obvious step is infinite dimensional spaces. And the obvious correlation would be functions. And indeed, it would seem like you could translate your high dimensional vector operations into functional operations. Like your XOR would be the addition of function f to the minus function g or something like this. And the question is, well, this actually prompts 2 questions. The first is, does anybody deal with the relationship between a functional representation of high dimensional vectors? And the second is, if I think about a function, I immediately think about some kind of regularity. Whereas one of the advantages of your high dimensional thing is that no regularity is necessary. But then one would ask, would some regularity, like some continuity or some whatever similarity in the dimensions or ranking of the dimensions or something, be helpful or deliver any information? I understand it's an extremely open question, but I excuse myself. This is the first time I come across this topic.
Yeah, no, that's a very interesting question. I'm not sure I got the right answer for that. For sure, there is a lot of literature. So everything started with Canerva with the paper of Canerva in 2009. And since then, just very few research groups around the world are working on this. I know there is IBM is also working on this. IBM with IBM Zurich in collaboration with ETH Zurich. They're actually working on also on the hardware. They are building very specific hardware, ASIC hardware, that is working specifically with vectors. And just recently, just a couple of months ago, they published a paper presenting a new hardware, a new CPU, able to work on these very high vectors, that is actually achieving, is actually faster than the fastest GPU of NVIDIA. So your questions are a bit tricky. Again, I'm not sure I'm able to answer.
Okay. No,
Maybe more. No, we can discuss that later. We can close the seminar, I think. Say hi to our guests.
Thank you very much. Goodbye then.
Ciao,
Thank you.
Andrea, grazie.
Ciao.
Ciao.
okay.
Ciao.
Awesome. Thanks, everyone.
Thank you, Fabio. Pezzo qua.